Good morning. Let's talk about some trig substitutions, specifically in relation to integrals. So this is probably, I think this is the last integration technique that we're going to go over for the AP exam. And this is by probably a fair margin the most difficult. If not the most difficult, then at least the most tedious. You don't have to necessarily be all that clever for these, but they can get kind of long. And so I would not spend too much time becoming masterful at these. And if you feel like, I'm so inadequate, I can't do trig substitutions, fear not, that's probably not the case. Well, you may be inadequate, but not for that reason. If you wanted to triage one thing to know for the AP exam, this would probably be a good candidate. It's good to understand how it works and kind of why it works, but becoming masterful and good at it, proficient if you will, it's not necessarily a good use of your time. So watch the video, kind of have a general idea of what goes on, and from there, move on with life. So we're going to start by jumping right in. This right here on the left is all you need to know. Well, okay, that's not true. But this is what makes trig substitutions work. And I'm going to present these as magic without any real derivation or particular justification. And they do need to be mostly memorized. So when you see something along the lines of a squared minus x squared, you let x equals a sine theta. Now, normally, you're used to being something like sine of theta equals x, and then substituting something in for x. This, you're letting x equal something, which is a little bit different than what you're probably used to, and that's understandable. The way I remember this one is using the mnemonic of sine. If you have a negative sign, and that's going to give you a sine theta. And then for the other one, so secant right here, which is 1 over cosine of theta. If the sign is not with the x, if it's with the other thing, whatever it is, probably a square. Everything's a square in life if you try hard enough. Then you say x equals a secant theta. And then if the two are added together, a squared plus x squared, then you say x equals a tangent theta. Now, as I said before, these kind of get cumbersome in terms of time, so they are difficult to test on the AP exam because you don't have a lot of time to take the AP exam. Granted, you have 4 hours, but that's a lot of calculus to cover in a relatively small amount of time, and so you're not going to be tested on this as thoroughly as you would in a university level class. I know the AP exam is supposed to show if you know enough show enough to get to pass a university level calculus class, but that's not entirely true. If you get a 4 or 5 in the AP exam, it's it's equivalent of an A or a B in a university level class. And depending on which university you're at, that's not going to be true. A lot of 4-year universities, they use the AP exam to basically qualify for a first or second semester engineering calculus class. And those classes are brutal. They're some of the most brutal classes you'll take because I think they're kind of used as a filter where if you can't, make past this hurdle, then you get washed out of the engineering program, which, right or wrong or whatnot, it's true, and it makes the classes fairly brutal. So if you can take the AP exam and skip those classes, you're better off in life. It's really important to know, it is fairly important to know calculus for engineering, but you really don't necessarily need to know it to the level that they teach and test to in the first 2 semesters of calculus at the university. So if you can bypass those classes, I recommend it. And it's these sort of problems is the sort of thing you'd see in those classes. You probably won't see this on an AP exam, at least not a problem like this. They might test it in some way. Okay, focus. So we have 9 equals 4x squared. And let's say we want to find the indefinite. I do not like orange. Okay, we want to find the indefinite integral of this. And we're like, okay, there's a negative sign associated with x. Ooh, but the form is wrong. We want the x squared. Okay, that's fine. But we're going to aim for the x equals a sine of theta. So we're going to start by rewriting this. Equals integral. We're going to factor the 4 out. So we'll do 4 times 9 over 4 minus x squared. It's really 4 over 4x squared. But 4 over 4 is 1, so I leave it off. And then, can we screw with this? Yep. So we square root everything. And then we can break the square root up so that it's square root of 4, because 4 is times everything, times the square root of 3/2 squared minus x squared. And we still have the dx. Okay, so now, then I'm going to take this. I'm going to change off orange to highlight my thoughts. And also, just to get away from orange, I don't know why I don't like orange. So square root of 4 is 2. And so now we have the form a and a. Still looks like a 2, I know. And x squared. A squared and x squared. And so we will go with the idea of x equals a, which in this case is 3/2, sine of theta. Therefore, dx equals 3/2 cosine theta? D theta? Okay. And then here, it's a good idea to draw a triangle. We really don't need it, at least not until later, but it helps me keep my thoughts straight. So we do good old SOHCAHTOA, where sine of theta equals opposite over hypotenuse. Equals, and then sine of theta equals 2x over 3, just rearranging this equation up here. And so we have theta here. This is a sad looking triangle. Opposite would be 2x, hypotenuse would be 3, and so this would be 9 minus 4x squared square rooted, using the Pythagorean theorem. Okay, so that keeps that straight. So now, let's dive a little bit more into this. So I'm going to bring this down here, just to give us a little bit more room and better manage the real estate. So we'll have 2 integral of 3/2 squared, true, minus, okay, this part's, so this is going to be 3/2 squared as well, because we are now substituting in sine squared of theta. And then all of this is square rooted, and then we'll multiply by dx, which we happen to know is 3/2 cosine theta d theta. Okay, doesn't seem so bad so far. Okay, probably do some canceling and moving around. I'm going to pull all of the scalars, constants out to the left. 1 minus sine squared theta square rooted times cosine theta d theta. Good for us. Good for us. Okay, so I pulled out the 3/2 squared, but I had to square root them to get them outside of the radical. And since there's a 3/2 in each of them, which was not accidental, that's why we chose x equals a sine theta. Sometimes when you see these formulas written, you'll see a b involved. Will be like a is 9 squared and b is 2 squared. I don't deal with b's. my memory is small enough that if I tried to remember an A and a B, it would just fall apart. Wouldn't work. Would not work. Okay. So now, cleaning this up a little bit, we'll have 9 over 2 times the integral. So this is where my notation is going to kind of go poorly. That's okay. So we know the Pythagorean theorem, sine squared plus cosine squared equals 1. So then 1 minus sine squared equals cosine squared. And so let's see here. So then we're going to have cosine squared theta integral the square root radical cosine theta d theta equals 9 over 2 integral of cosine squared theta d theta. And we know how to do this from previous lectures. So you're probably thinking then like your heart sinks a little bit because like, oh, we're going to have to do a double angle formula. Indeed, this is going to call for a double angle formula. So let us recall our double angle formulas. Can I recall them? I don't know. I'm not nearly as smart as I like to think I am. That was going to be a parentheses, but then I changed it to a C. Saw how I did that? Yes. Bush League amateur. All right, 1/2 cosine of alpha minus bravo plus cosine of alpha plus bravo. Okay, I'm going to write the other two up just so that I have them. So let's see, if we had sine alpha times sine bravo equals 1/2 cosine alpha minus bravo, and then we do negative sine because the sine is all that changes, cosine alpha plus bravo, and then we have one sine and one cosine. We'll do sine of alpha, sine of cosine of bravo. Then we change to sines. Sine of alpha minus bravo plus, because it's going to be like the first one again, sine of alpha plus bravo. There we go. So the one we're going to have to use is the top one because we have a cosine squared. And then we're going to say, well, see if I can get all of this in view. I probably can't. So if we say alpha equals bravo, then we're going to have cosine of theta squared equals 1/2. And then alpha minus bravo, if alpha equals bravo, then that's just going to be cosine of 0, which is 1, plus cosine of 2 theta. Cosine of 2 theta. That was terrible. Cosine of 2 theta. There we go. And so, yeah, that's exactly what it is. So let's do 9/2 integral 1/2 1 plus cosine of 2 theta d theta. Can we solve this? Yes. Yes, we can. Just move out the 1/2. So this will be 9. Okay. So I'm going to do a little sidebar and solve integral cosine of 2 theta. Now, I'm pretty sure that it's just sine of 2 theta over 2, but I'm not that sure, so I'm going to do it more methodically using the substitution. 1/2 du equals d theta. Okay. So we have integral 1/2 du cosine of u equals 1/2 sine of u. Okay, plus c. Okay, and the derivative of sine is cosine. The sine stays the same, so that's true. Which is 1/2 sine of 2 theta plus c, which is sine of theta over 2. Okay, so my intuition was correct. It is about half the time. It's like plugging in a USB cord. It's like, you never get it the right angle. You just turn it upside down. Never get it on the first time, even though it seems like it should be 50-50 chance. Okay. So this is going to be 9/4 theta plus sine of 2 theta over 2. And then there's a plus c. Okay? So now our thoughts are, well, we started with what, x's? And we want to get back to x's. So we took the integral, but this really doesn't make that much sense yet. We should return things the way we got them. So we're going to do another double angle formula, which we wrote up over here already with the double signs. So I'm going to write this out. You can see how these get convoluted. Nothing's really all that hard, but man, gee willikers. Sine squared of theta equals 1/2. No. We need to use the bottom one because we have sine of 2 theta, which is this. Okay. Equals sine of theta cosine of theta equals 1/2. And this will be sine of 0, which is 0, plus sine of 2 theta. There we go. There's our half angle formula. So sine of 2 theta equals 2 sine theta cosine theta. Okay. I'm going to just memorize that briefly. Bring it over here. So, see if I can remember this. My short-term memory is working at maximum capacity. Theta plus 2 sine of theta cosine theta over 2. And then there's still a c out there. Okay. I'm going to make sure that's right. 2 sine theta. Okay, we got that. Okay. I'm going to clean this up a bit just because there's a lot of stuff here. So, get rid of that. Get rid of this. Get rid of a little bit more of that. Get rid of the substitution. Most other stuff is kind of useful though. Okay. So I cleaned up a little bit. So now, maybe this is everything we need. Is this everything we need? Let's see if this is everything we need. Okay. So, it might be. Okay. So now we're going to convert these back to x. And it's not going to be pretty. So, start by canceling out the 2's and feel as if I did something productive. I did not. 9/4. So, start with theta. So, we go back up here and solving for theta, we have 2/3 x equals sine of theta, which I guess we kind of already knew. So theta equals arcsine. Some people use the little -1 symbol. I don't like that because, or I try to avoid it generally when I can, because I get that confused with 1 over sine theta as opposed to arcsine. So I use the arcsine instead of the sine -1 just because I think it's less ambiguous. So arcsine 2/3 x. Okay? I'm going to write it with a capital A just to show how proud I am that I actually kind of got this. Oh, but then I forgot that, is it 2/3 x? I think it's 2/3 x. And 2/3 x. Okay, we're good there. Plus, now we have sine theta times cosine theta. So we already have, we know what sine theta is. Sine theta is 2x over 3. So now for cosine of theta. So cosine of theta, we can do the same way. Red. So cosine of theta equals SOHCA adjacent over hypotenuse, which from our diagram we now know is 9 minus 4x squared over 3 square rooted. 9 minus 4x squared. 9 minus 4x squared over 3 square rooted. And then, ooh, plus c. I got that one. I guess I could probably put the plus c inside the brackets because it's just a constant and can be multiplied by 9/4. Doesn't matter. Okay. So, this thing, which looks terrible, is probably close to the answer. Let's Wolfram this one. So 9 minus 4x squared, square rooted. Integral of square root of 9 minus 4x squared. See what happens. See how close we were. Okay? So we got 9 arcsine. So it did have an arcsine of 2/3 x. There's 9/4. Yep, okay. Yeah, we got that part. And then I think is there an extra 9 involved in that? I don't, there's something going on there. Oh, maybe they canceled the 3's? Maybe. I'm going to count this one as a win. Interesting. Maybe I missed, I don't know. Ah. Right here. That's part of it. That becomes 9 and that cancels with that. Because the 9 minus 4x squared, the square root part's only on the top. So, yeah. I'll count that as a win. I'm impressed I was able to get through that. So, if it wasn't obvious to you before, this is why you will not see too many of these in the AP exam. It's just too involved. Too much stuff. And there's a lot of trigonometric identities involved, but there's really not that much calculus involved. Well, there's a reasonable amount of calculus, but it's not as emphasized as figuring out how to go through all the trig identities. Okay? But that's about, it's not as complicated. These can get pretty good. So I'm going to show you a couple more examples. One is an example of what not to do. So we got 9 minus 4x squared. So we're going to see another one like this. So let's say, for example, you have, lock that in place. Okay. So we have, let's see, ooh, gray, dark gray. So we have x over, and we'll do dx and integral. And we're thinking here, so we have a couple of squares underneath the radical, probably trig substitution. Yes, but let's not. You probably could solve it through trig substitution. I would not recommend trying. Instead, what you want to notice is substitution. You have one portion that is a derivative of the other portion. So what you would do here then is you would say, instead of going with the trig substitution like we did before, if possible, just do a normal substitution. So you'd say u equals 9 minus 4x squared du equals negative 8x dx. Negative 1 over 8 du equals x dx. This then becomes integral 1 over u square rooted times negative 1/8 times du. Rewriting that a little bit, we have negative 1/8 integral u to the negative 1/2 du. Using the power rule, we have u to the positive 1/2 over 1/2 plus c. And let's see here. This then probably the negative 1/2 dividing by 1/2. Negative 1/4 square root of u plus c. And see, I was able to do that in seconds as opposed to a multitude of minutes. Dozens of minutes? A couple dozen minutes. So the idea here is if you come across a trig substitution problem on an AP exam, first thing you should do is make sure it's actually a trigonometric substitution problem and not something like a U substitution problem. Okay, we're going to do one more authentic trigonometric substitution problem just to kind of get the idea down. Well, yeah. Oop. Go away. Unlock. Delete. Move on. There we go. Not as fluent with this as I would like to be. Okay. So, we're going to jump on this horse. Ooh, blue. Blue's always a good way to start off a problem. All right. So, we have the minus on the not x term, so we're going to use secant. Yes. So we're going to start by saying x equals, and it looks like 5. Yep. 5 secant of theta dx equals, do I know the derivative of secant of theta? Oh yeah, of course I do. These aren't integrals. I can do any derivative. Okay. So 5 over cosine of theta. Nope. We're going to rewrite this as d theta of times 5 cosine of theta to the negative 1. Use the power rule. Power rule? Yeah, probably power rule. And chain rule. So 5 times cosine of theta. Negative 1 goes down a little bit to negative 2. We took negative 1 down here. Times the derivative of the inside. Derivative of cosine is sine of theta, but that's negative. So that makes that a positive. So this equals 5 sine of theta over cosine squared of theta. Okay. So come back here. 5 sine of theta over cosine squared of theta. D theta. Make that theta. Erase this just to preserve real estate. Okay. 5 secant of theta. Okay. I'm going to Wolfram that. Okay. Derivative of 5 secant of x. Tangent of x, secant of x. And we have here tangent of x, secant of x. Okay, good. I agree with that. All right. So now we've got our first half of the step done. Then we'll draw our triangle. What kind of... Is it sad that the part I find most interesting here is which color to choose. Probably is sad. Oh. And my biggest disappointment in this is my inability to draw triangles. Okay, so x over 5 equals secant of theta, which equals 1 over cosine of theta. You know from SOHCAHTOA that cosine of theta is adjacent over hypotenuse. So this would be secant is hypotenuse over adjacent. So hypotenuse is x, adjacent is 5, and that gives us x squared minus 5 squared square rooted. Hypotenuse over adjacent. Okay, yep, I'm good at that. And that's our triangle. And now we start substituting things and seeing what happens. Hopefully something wonderful. So, make this a formal. There we go. Big line. So x squared would be 25 secant squared of theta. 25 secant squared theta minus 25 square rooted. And then on the top, we're going to have 5 sine of theta times, then I'm just going to write the cosine squared divided by cosine squared of theta as secant squared of theta, which is convenient because I think they cancel out. Okay. Yep. And this will be integral d theta. And I'm going to clean this up slightly. So first thing I'm going to look at is, we know from the Pythagorean theorem, sine squared plus cosine squared equals 1. We divide everything by cosine squared, then we get tangent squared plus 1 equals secant squared. So what we're left with then is, so this will be 5, these secant squareds will cancel, and we have a sine of theta over, and we'll bring out a 5 times the square root of, secant squared minus 1, secant squared minus 1, and I just, because I factored out the 25, and then you take the square root of 25 and get 5. I guess that was 10. 5. Tangent squared theta, d theta. Okay. And make it a little bit prettier one more time, maybe 2 more times. Sine of theta, d theta, 5 tangent of theta. And we know that tangent of theta is sine over cosine. So this would be 5 sine over cosine times sine. And I left off the thetas here. I should put them in. Cancel, cancel. And this equals integral 1/5 cosine of theta d theta. Wow, that worked out well. Quite fortuitous, one might even say. Ooh, that's the tough part. Okay. I know it's going to be sine. So the derivative of sine is the positive cosine of theta. So the signs will be the same. Yes. Plus c. And now, since we started with x's, it's only fair in life that we go back. Life isn't fair. I'm not sure why I'm trying to make it fair. Okay. So sine of theta equals, from SOHCAHTOA, opposite over hypotenuse, which also equals x squared minus 25 square rooted over x. Okay. Equals x squared minus 25 square rooted over 5x plus c. Yeah, that was much easier than the first one. That actually worked out fairly well. Good for us. Good for us. Okay, now I'm going to verify real quick just to make sure I didn't go completely out of line. So let's remember, what was the x squared minus 25? Okay. Integral of 1 over quantity x squared let's do x squared times square root of quantity x squared minus 25. And then 1, 2, 3 parentheses. All right, let's check this out real quick. X squared minus 25. Yep, that seems reasonable. Go Wolfram Alpha. I love Wolfram Alpha. Did I miss a 5 somewhere? Outrageous. I guess I shouldn't have verified. I should have just said with confidence. And maybe someone would have believed me. Oh, wait a sec. Opposite over hypotenuse. Yeah, I wonder where I lost that 5. It's probably, was it that 5? No? Interesting. Yep, nope, I definitely missed it. Missed something there. Outrageous. Well, I'm not going to hunt it down because if I was confident I would have just got it the first time. But alas, we see that that is not to be. So there was a lone 5 that escaped the herd. I'm a poor shepherd of 5s. Poor shepherd. Okay. So I'm sure there's plenty of people out there that'll be able to times 5. Correct me and let me know when where I'm wrong. Okay. So that's the idea behind trigonometric substitution. It should be avoided when possible. It just gets a little bit more complicated and involved than you want to be. This takes more focus than you want to give to any single problem for an AP exam. So if you can not do trigonometric substitution, I'd recommend not doing it. But as a last resort, if you have time, maybe skip over that problem, come back to it at the end. Might as well start working through it. And if you have nothing else better to spend your time on, it's a good chance. But it's the secret to trigonometric substitution is just memorizing these 3 thumb rules. And again, the way I memorize them, or mnemonic them if you will, is you have a minus x squared square rooted. If you see that, then the sign with the x tells you that you're supposed to use sine. If the sign is with the a squared, then it's going to be secant. X equals a secant of theta, where secant is 1 over cosine. And then if they're added together, they're going to be tangent. And that kind of sort of makes sense, because when you start seeing the triangles, it means that the biggest part's going to be, you think of the 2 legs of the triangle added together, and that is the tangent. All right? Sounds good. That covers pretty much all the techniques of integration we're going to come across. Now we're going to start using these techniques of integration to actually do things that are more useful. So, sounds good. See you next time.